Arithmetic group. History. One of the origins of the mathematical theory of arithmetic groups is algebraic number theory. The classical reduction theory of quadratic and Hermitian forms by Charles Hermite, Hermann Minkowski, and others can be seen as computing fundamental domains for the action of certain arithmetic groups on the relevant symmetric spaces. The topic was related to Minkowski's geometry of numbers and the early development of the study of arithmetic invariant of number fields, such as the discriminant. Arithmetic groups can be thought of as a vast generalization of the unit groups of number fields to a non-commutative setting. The same groups also appeared in analytic number theory as the study of classical modular forms and their generalizations developed. Of course, the two topics were related, as can be seen, for example, in Langland's computation of the volume of certain fundamental domains using analytic methods. This classical theory culminated with the work of Siegel, who showed the finiteness of the volume of a fundamental domain in many cases. For the modern theory to begin, foundational work was needed, and was provided by the work of Armand Borel, André Weil, Jacques Tits, and others on algebraic groups. Shortly afterwards, the finiteness of convolution was proven in full generality by Borel and Harish Chandra. Meanwhile, there was progress on the general theory of lattices in Lie groups by Atul Selberg, Grigory Margulies, David Kazhdan, M.S. Raghunathan, and others. The state of the art after this period was essentially fixed in Raghunathan's treatise, published in 1972. In the 70s, Margulies revolutionized the topic by proving that in most cases the arithmetic constructions account for all lattices in a given Lie group. Some limited results in this direction had been obtained earlier by Selberg, but Margulies' methods, the use of ergodic theoretical tools for actions on homogeneous spaces, were completely new in this context and were to be extremely influential on later developments, effectively renewing the old subject of geometry of numbers and allowing Margulies himself to prove the opposite. In another direction, the classical topic of modular forms has blossomed into the modern theory of automorphic forms. The driving force behind this effort is mainly the Langlands program initiated by Robert Langlands. One of the main tools used there is the trace formula originating in Selberg's work and developed in the most general setting by James Arthur. Finally, arithmetic groups are often used to construct interesting examples of locally symmetric Riemannian manifolds. A particularly active research topic has been arithmetic hyperbolic definition and construction. Arithmetic groups using number fields. Examples: arithmetic lattices in semisimple Lie groups, the Borel-Harish-Chandra theorem, Margulies' arithmeticity theorem, arithmetic fusion and Kleinian groups, classification, the congruence subgroup problem. A congruence subgroup is roughly a subgroup of an arithmetic group defined by taking all matrices satisfying certain equations modulo an integer, for example the group of 2. These are always finite index subgroups, and the congruence subgroup problem roughly asks whether all subgroups are obtained in this way. The conjecture usually attributed to Jean-Pierre Serre is that this is true for irreducible arithmetic lattices in higher rank groups and false in rank 1 groups. It is still open in this generality, but there are many results establishing it for specific lattices in both its positive and negative cases. Arithmetic groups. Definition and definition. Lattices in Lie groups over local fields. Some applications: explicit expander graphs, arithmetic groups with Kazhdan's property T or the weaker property T \displaystyle \tau of Lubotsky and Zimmer can be used to construct expander graphs Margulies or even Ramanujan graphs Lubotsky-Phillips-Sarnak. Such graphs are known to exist in abundance by probabilistic results, but the explicit nature of these constructions makes them interesting. Extremal surfaces and graphs. Congruence covers of arithmetic surfaces are known to give rise to surfaces with large injectivity radius. Likewise, the Riemannian graphs constructed by Lubotsky-Phillips-Sarnak have large girth. It is in fact known that the Riemannian property itself implies that the local girths of the graph are almost always large. Isospectral manifolds, arithmetic groups can be used to construct isospectral manifolds. This was first realized by Marie-France Vigneres, and numerous variations on her construction have appeared since. The isospectrality problem is in fact particularly amenable to study in the restricted setting of arithmetic manifolds. Fake projective planes. Projective planes